So in this section, our goal is to find the length of a curve using the similar idea that we did in Calc 1, where we found the area under a curve. So what we do is we look at small divisions and then just add up all the pieces to get the length of the entire region we're interested in. So what's the idea? Let's say I have a curve f of x and I want to know how long that curve is. So I'm interested in the length. In other words, it's like a piece of string. How long really is it? I can say, well, it's approximately that long if I just use one segment. But we know that's a pretty bad approximation because this guy is longer than that just straight line. So then we say, okay, let's improve that a little bit and maybe look at it as this and that. Well, that's a better approximation. I'm looking at this segment and that segment added up together, and that length is closer to the curve length than it was with just one segment. Or we look at, I don't know, let's say 3 pieces. From here to here, I calculate how long, from there to there, and then from there to there, and you notice with 3 of them, I am approximating the length of the curve even better. So the idea is that we look at small divisions and add up all those segments to get a better approximation of how long that curve is. So, a not so great approximation of the length, doing a little better, doing even better in this case. So let's go and look at the rough idea of how we develop the length of a curve, or rather the formula for the length of a curve. So here I have a function from a to b, and I've chopped it up into small segments, and for each segment I am looking at the length of the curve in that little small subinterval, trying to approximate how long that piece is. So I'm going to go to the ith interval and zoom in on it, and it's going to look roughly like this. It's going to look almost linear, the little piece that I'm interested in, and I'm going to make a right triangle out of it, and this segment we know is a delta x because we were making equal subintervals, and approximately this guy is a change in the y values. So we got a change in the x values and a change in the y values, and this is approximately looking linear, and I'm interested in the length L. So using the Pythagorean formula, we have that L is approximately a squared plus b squared under the square root to give me the length for c. So L is approximately the length of this little black piece of curve that I'm interested in, but I am kind of approximating it with a line. So L, this little black segment that we've really zoomed in on and acts almost linear, is approximately this guy over here. And we're just going to go do some algebra with this now. So I factored out a change in x squared out of these two terms, and I ended up with 1 plus, if I'm factoring out a change in x squared, then that means I'm dividing it by this term. So that when I distribute this back, I get the change in x squared, and when I distribute this back, the change in x squares cancel, and I get back to wherever I was before. So all I did was factor out a delta x squared. Now this is delta x squared times this other business, and delta x squared is just a positive term squared, and since I'm taking its square root, I can have it pop outside the radical. So I took the square root of the first piece, that popped out as delta x, and radical all this other garbage that's still under the radical. Now notice what we get here is basically delta y over delta x, quantity squared. So let me rewrite it like that. And notice delta y over delta x. What is that really? What do we know change in y over change in x normally as? It's a concept we're familiar with. That's simply the slope, right? The slope of a line at that point that you're interested in is delta y over delta x. So it's just a slope, and for the small interval we're interested in, we know that the slope is really f prime. It's the derivative of f at that point in the ith interval that we're interested in. So we're going to rewrite this as delta x times 1 plus basically f prime squared at some point in that little ith interval. We'll call it x sub I star, let's say. So it's just 1 plus f prime squared. So next, we add up all these little lengths, the little L that we're approximating, all of these little lengths through this process, and we let n go to infinity, and we ultimately get the formula for the length of a curve. So the length of the curve from a to b, the integral from a to b of 1 plus f prime squared dx basically gives us how long this guy is from a to b. And we got there through the process of approximating little segments and then letting n go to infinity and adding up a whole bunch of them and getting to the integral. So this is the important idea, but we can look at this in two different ways. So we may be given the curve as a function of x or a function of y and asked to find the arc length for it. In other words, the length of that curve. So depending on whether it's a function of x or a function of y, this formula may look a little bit different. It's the same thing really, same idea, but we'll go ahead and break it up into two types, type 1 and type 2, depending on which case is given to you. Although they're interchangeable, you can take this possibly and put it in as a function of y, or look at this as a function of x, but let's just go look at the two types. So type 1 is exactly what we looked at before, from a to b, 1 plus f prime of x squared dx, or sometimes you may be seeing that formula written in Leibniz notation, dy over dx squared, which is the same as f prime squared. So that'll be a dx problem. First of all, let's pay attention to that. And that means your limits of integration would have to be x values. So something to watch out for. If you're dealing with a function of x and doing a dx integral, you should have x values for limits of integration. And this type is usually used when it is easy to isolate y. So basically you have y as a function of x. So if it's the curve that's given to you, if in that curve it's easy to solve for y, or it's a function of x, then you're probably going to be setting up an integral of type 1 and doing a dx problem. Type 2 we'll say is where you're given a function of y, so you take its derivative and you end up dealing with a dy integral. So if you're dealing with a dy integral, again, g prime of y, the same thing as dx over dy if you're using Leibniz notation. And the one thing to pay attention to is that if you're doing a dy problem, you better have your limits of integration as y values. And normally you use this if it's easy to isolate x in your problem. So you'll have x as a function of y basically. So these are the two things we're going to keep in mind. We're basically going to have 1 square root of 1 plus f prime squared. That's the thing to keep in mind. If it's easy to isolate y, you're probably going to do a dx problem with limits of integration being x values in your curve going from a certain x to another x. And if it's easy to isolate x in your problem, you're going to have a function of y, and you're going to set up a dy integral having y values for your limits of integration. Aside from that, just keep in mind all you're doing is differentiating, plugging it in here, and then analyzing the integral that you have to deal with. So let's go look at some examples. Okay, so this problem says find the length of this curve over the interval 0 to 2. So right off the bat, I know that y is isolated, which means I'm probably going to set up a type 1 because y is already isolated for me. Why should I do more work than I have to? So first thing I have to do is find f prime, or find the derivative of that function. So I take the derivative of this function of x. Y prime is 1/2 4 minus x squared to the negative 1/2 times negative 2x. Remember to apply the chain rule. Let's clean it up a little bit. Once I have my f prime, I need to square it to plug it into my arc length formula. So let's square that guy. So I took f prime, I squared it, and that's what I got. Then I simply use it in the formula we developed from a to b, and I'm doing a dx problem. And they already gave me over what interval. From 0 to 2 are my x values. So from 0 to 2, 1 plus f prime squared, which I got here, I put it in there. Now I'm going to do some algebra to clean this up a little. So I'm going to get a common denominator. So multiply the 1 by 4 minus x squared top and bottom. Get the common denominator 4 minus x squared. We got 4 minus x squared plus another x squared. Cancel the x squares. And now we're up to here, and let's maybe split the radical into a top and bottom and take out something outside. So square root of top over square root of bottom, and that pops out at 2. I'm going to pull it outside, and I have 1 over the square root of 4 minus x squared, which pretty much looks like a trig sub. So let's apply a trig sub on it quickly. So x is 2 sine theta, it fits that form, and dx is 2 cos theta d theta. Let's replace our dx and replace our x, and I'm going to go ahead and change my limits of integration right now also so that I don't have to worry about going back to x's. So using the trig sub x equals 2 sine theta, over here x was 2 for the top limit. I put in a 2, I divided both sides by 2, sine theta is 1, take sine inverse of both sides, and we know that the angle pi over 2 has a sine of 1. So the top limit is pi over 2. Similarly, if I put x to be 0, in my trig sub, I have sine theta equals 0, and what angle has a sine value of 0? That would be the angle 0. Let's factor out a 4 from downstairs and change this guy to, I guess, cosine squared theta. This is a product, so I can split it. Square root of 4 is 2, and square root of cosine squared is cosine theta on the interval of interest. These guys go away nicely. I just get 1 d theta, and 1 goes to theta. I had a 2 outside, so that's 2 theta from 0 to pi over 2. Let's go plug them in. I don't have to worry about changing these back to x's because I already took care of my limits of integration with my trig sub, and I changed them in terms of thetas. So after I evaluated, it looks like the arc length that I was interested in is pi, meaning between 0 and 2. This guy has an arc length, or a length of, that curve has a length of pi units. Now let's see if this makes sense by looking at the problem another way. What were we really interested in? We wanted the arc length for this guy over 0 to 2. Well, we should be familiar with this guy, what the shape of this really is. This is a semicircle. This really comes from, if I were to square both sides, this is really y squared equals 4 minus x squared, and if I move the x squared to the left, I'm simply looking at a circle of radius 2, centered at the origin, if I were to clean up that curve that I was looking at. But they wanted the arc length of this curve, which is just the top part, right? That's just the top part of this circle of radius 2. And they wanted it over 0 to 2. So we're just interested basically in this arc length over here. If I were to go look at it geometrically and not apply the arc length formula, well, we know that's just 1/4 of the entire circumference of this circle. And we know that the circumference of a circle is 2 pi r. We know the radius here is 2, so 2 pi times 2, which is 4 pi. But we don't want the entire circumference, we just want 1/4 of it. So 1/4 of the entire circumference is going to be just pi, which is exactly what we found using the arc length formula. So this was a familiar shape, and we could kind of check it out to see that things do make sense, that between 0 and 2, that arc length developed is pi units. So that's just the first example to get a feel for how the formula got developed, how you use it, and how things kind of make sense if we can double check things with things that we're familiar with already. In the next video, we will just look at more examples.